So, welcome to the 8th week of live interactive session on the course integral transforms and their applications. So, here I will be solving demo problems according to the contents for that particular week. So, this week we will be looking into specifically Legendre transforms, and we will revisit some more problems if we have time for the earlier week, that is Hilbert transform and stageless transforms. So I will be showing some demo problems and explain how to solve them. So this will help you to understand the concepts better and also solve the assignment problems easily. So we will start now. So I have the first question. If x equal to a by root t and y equal to a by t raised to 3 by 2, where a is some constant, then which of the following is correct regarding the solution of the integral equation? So an integral equation is given, which is f of s is equal to 1 by square root of pi integral 0 to infinity exponential of minus st f of t dt. So let me tell you this is actually not related to Legendre transform or nothing. It's basically Laplace transform that you may have figured out when you've seen this particular factor. The kernel is actually exponential of minus st, right? So which is related to Laplace transform. Why I include this question is that so for the last week, if you have watched the lecture videos that the professor have explained, the similar problem where the kernel was 1 by s plus t. Basically, it's related to the Hilbert transform. So I thought this problem is nice in that sense. I mean, we can use the same methods here as well. Just the kernel is different. So the same thing, the similar question you can expect from other transforms as well. You have an integral equation where the function is appearing both inside and outside, and you have to solve for it. So same technique you can use. So here I will show it for Laplace transform, and you may expect similar question for Legendre transforms as well. Okay, so let us start. So thing is that options are also given, and says that x and y are suspected solutions. Either x or y or both or neither can be the solution. So you can try them out and check whether it works or not. And if you just observe, x and y have the same format, right? So it says that f of t can be a solution. So f of t can be x or y or both or neither. Both have the identical format like a times t raised to alpha, where alpha is equal to minus half minus 3 by 2. The given options. So we just want to, we can substitute and check whether it is working or not. Another way is that you substitute for alpha and check for whether it is working in this particular equation 1 or not. And another thing you can try is that in generally you can keep alpha as such and solve for alpha, so that whatever alpha you are getting, all the values of alpha, you can say this particular form 2 is a solution. Okay, so we'll start that. So RHS of 1, we will substitute the expression 2. Okay, so that is 1 by square root of pi integral 0 to infinity 0 to infinity exponential of minus st, then the function which is a t raised to alpha dt. So now a is some arbitrary constant. Okay, so we will take the constant outside. Also we can do one thing. See, this is actually Laplace transform, so you may already know the solution for this particular Laplace transform, which is Laplace transform of t raised to alpha. You know that, right? But still you can convert it to another non-integral, which is a gamma function. So you can substitute st equal to u, so that s dt is a du. So now you take the constant outside. Now the integral, again the limit is not going to change because of this substitution, which will be 0 to infinity again. Now exponential of minus st is just minus u, then t is just u by s, the whole raised to alpha, then dt is du by s. Okay, now you take the constants outside. According to the integral, the constants are s, right? S, alpha, everything is constant. So s raised to alpha plus 1 we can take outside. The integral is just becomes 0 to infinity exponential of minus u raised to alpha du. Yeah. So this is just alpha factorial, or in general real value of alpha you will say it's gamma of alpha plus 1. Okay, so it's a by square root of pi gamma of alpha plus 1 by s raised to alpha plus 1. So this is what we got from the RHS. Okay, so we substitute the expression 2. So that's what we got from the right hand side. So LHS of 1 says that f of t, okay, here also we substitute 2 in the LHS of 1, which says that f of s, okay, sorry, yeah, we LHS is supposed to f of s, right? So it's f of s. If you do that, it is a into s raised to alpha. Okay, because the f of t was a t raised to alpha. Now we are doing f of s, which is a s raised to alpha. So now thing is that LHS should be RHS. So we want LHS equal to RHS. So that means a s raised to alpha should be equal to a by square root of pi gamma of alpha plus 1 by s raised to alpha plus 1. So we can take the alpha, which is an arbitrary constant, right? And you group together the terms containing s, because s is a variable, right? So you bring this s raised to alpha plus 1 on the left hand side till we become s raised to 2 alpha plus 1, and keep the constants somewhere, because alpha is a constant for this when we want to solve for alpha, but alpha is a constant. And you see the this will work. So we have to solve for we have to find alpha. So let's say this equation is 3. From 3, so right hand side is actually a constant, and left hand side is a like a function of s. It had dependency on s, but we don't want it because right side is a constant. So that 2 alpha plus 1 should be equal to 0, which says that alpha should be equal to half. So this is from the left hand side. But see, the right hand side is a constant, and that is a particular constant. See, when we put 2 alpha plus 1 equal to 0, that means LHS become 1 because it's s raised to 0. So the right hand side we want it to be similarly 1, which means gamma of alpha plus 1 by pi should be equal to 1. So that means gamma of alpha plus 1 should be equal to root pi, and for alpha equal to minus half, gamma of alpha plus 1 indeed root pi. So alpha equal to minus half is a solution, or is the possible solution. Thus we find that f of t equal to a t raised to alpha, which is equal to a t raised to minus half, is the solution, or is one of the solution. Let's say a solution, because what we have done here is that we assume the form of the solution to be a t raised to alpha, and for that particular form we found that when alpha is minus half, there is a solution which is a t raised to minus half, or a by root t, and here it is given which is x, right? Yeah, x is the solution, because alpha cannot be minus 3 by 2, so y is not a solution. But see, this is a particular form that we have assumed. The form of the solution is a t raised to alpha because we have given some options in the question, x and y, right? There can be another form of the solutions that may include log and r, so that we may need to use some other methods. So this is like a substitution. I mean, we a priori have some idea of how the solution will look like. That's why we substituted and check. Okay, so is this clear? Any questions on this? Okay, if no questions, we will move to the next question. Um, yeah. So this is based on Legendre transforms. So find the Legendre transform solution of the Dirichlet boundary value problem for the function u of r comma theta, where u r r, which means the second derivative of u with respect to r, plus 1 over r u first derivative with respect to r, plus 1 minus x square u xx minus 2x ux is equal to 0. So r is bounded between 0 and a. So it's actually a finite domain which is extending from 0 to a in terms of the radial coordinates. And theta is an angular coordinate which is extended from 0 to pi. So where theta is like x equal to cos theta, from there only it came. So the actual parameter supposed to be theta, we substitute it like x equal to cos theta, so that the differential equation we can write in terms of x, so that the function also we can express in terms of x, so that u of so basically the boundary condition is given like u of a comma theta, which is any value of theta, the function value, that u value of u at r equal to a, the other boundary, is given to be f of x. So it's like it's actually should be a function of theta, but theta is a function of x also, right? Because theta is just cos inverse of x. So we'll get effectively a function of x for every theta which is less than pi and greater than 0. And also we want solution to be finite everywhere. That's another criteria that remember always. Okay, even though it is not given here, see, you have only one boundary condition given, so you need other boundary conditions as well, right? So because even in x, you see it's actually secondary to x. So both in x you need both in x are also in r you need two boundary conditions, but at least you need a two boundary condition in x to get the solution in the transformed coordinates at least. But you only one is given, because other is not given, because that automatically you can assume it should be bounded. So while solving we will see. So let us start anyway solving this problem. So let me write the equation again. It's dou square u by dou r square plus 1 over r dou u by dou r plus 1 minus x square. So we can actually substitute that and we see how the equation actually look like. It's actually sine square theta. Yeah, that you can actually try. So because we don't need to write that in that coordinate, so I am just writing in the transformed coordinate x equal to cos theta. So 1 minus x square into dou square u by dou x square minus 2x dou u by dou x equal to 0. So where x equal to cos theta and r is limited from 0 to a, theta is limited from 0 to pi. That means x is limited from minus 1 to plus 1. Okay, so now this is the equation. Let's say this is equation 1. Now we have to use a Legendre transform, right? So we have to take the Legendre transform where u is actually a function of r and theta, but which is equivalently a function of r and x also, because theta is a function of x. We are going to take the transform in x, and then we will write it is u tilde of r. So the transform, Legendre transform, will take from the variable x to n. The Legendre transform I will represent using the curly f, this symbol. I am not sure what to call it. Okay, using this symbol. So so that it will transform the variable u, so the parameter u, the quantity u, which is a function of r and x, to u tilde, which is a function of r and n. So equation 1, if we take the transform, we will get like I have explained earlier, because it's a bi-variable function, you have a partial derivative in both the variables in equation 1. Now when we take the transform, in the transformed variable there is no derivatives going to appear. It will be algebraic in the transformed variable. The other variable derivatives will remain, but if you see in terms of the derivatives, there is no extra derivatives appearing. It's like the other variable is treated as a constant. The transformed variable is a constant with respect to the remaining derivatives. So it is basically getting converted to an ordinary differential equation in the remaining variable. So here the transform is happening on the variable x. So the remaining variable is r. So in that variable, the equation will be just a ODE. So that's why we don't need to write the partial derivative. We can write the ordinary derivative here. So it's a d square u by dr square. Sorry, u tilde, because after the transformation. Remember, u tilde is this. It's a function of both r and n. It's actually multi-variable function, but still the derivative is only appearing in the parameter r. Then again 1 by r du tilde dr. Then see this parameter, this quantity is actually r, right? So if you have watched the videos, this is represented using r, the r operator acting on u. Basically it's actually 1 minus x square dou u by dou x is acted by dou by dou x again. So that has a property, because it's transform in the after its Legendre transform, it will just simply convert it to minus n times n plus 1 times the transform of the function u itself. Given some certain conditions need to be satisfied, that u should be the function u and its derivatives should be bounded at the extremes. So we always assume that will happen, and thus we will proceed. And in actual case, you have to make sure it will happen. Here it's a demo question, it will happen, of course. Okay, so I guess you know how to do that, like the function u, first derivative, and u. So you have to make sure they will vanish. So I think it would also multiply with 1 minus x square, both of them, in the limit of the x tending to plus or minus 1 should vanish. So that you have to show. So if you have watched the lecture videos, it's clearly during the derivation it has shown that how we need the boundary conditions to vanish, so that this expression will, that is the transform, will be just equal to minus n times n plus 1 times the transform of u itself. So that is shown in the lecture videos. You can watch that. Okay, so this is a transform of the equation 1 in the left hand side. In the right hand side, it is just 0, so you get 0. So now this is the equation. So see, in the lecture videos, there is a similar equation has already solved. So now it become an ODE. It's actually a second order linear differential equation. You can actually, but not with the constant coefficients, remember. So this is actually a special equation. So if you multiply throughout by r square, still the equation is valid. Remember, when r is not equal to 0, you will get something like this, as r into du tilde by dr minus n into n plus 1 r square u tilde equal to 0. So you have an identical condition in similar equation is solved in the lecture videos as well. So where the equation was a little slightly different. You don't have this r square here, so that's just a constant there, n plus 1. So there it is actually easier. The equation is the solution we know. This has a particular form of solution. You can approximate it as r raised to alpha is a form of the solution, and you will solve for values of alpha. So that's the usual procedure. But here that is not possible, because our equation has an r square here. So it's r square here, r square is here also, then r into first derivative. So this particular form of the solution actually resembles the Bessel equation. So this is actually a Bessel equation, but it's a modified version of the Bessel equation. So the actual Bessel equation will be something like y, let's say I'm having a function y, and I'm taking derivative with respect to r. So y double prime. So prime I am using to denote the derivative. Then y prime by r. Uh, then plus 1 minus n square by r square y is equal to 0. We'll have solutions y. Two solutions will be there, orthogonal solutions. One of them will be Bessel n of r, other one will be yn of r, Bessel yn of r. Now I have modified, so this is a Bessel equation. So Bessel differential equation. Now modified version is actually, so you will have I is changing to so R will change into IR, the complex case. So that time you will find this is a y double prime, because it's a second derivative, you will have a minus 1, because you see this is actually going to be yeah, so d square y by dr square, that's the first derivative. Now you will do this transformation, you will have an I square coming along, so that I square will give a minus here. Similarly, that minus will come here as well, the second time also. The third time also you will have the minus r square will come. Yeah, it's correct. So you will have basically minus y double prime, then minus y prime by r, then plus 1 minus n square by minus r square. So that will make it plus r square equal to 0. Now you rearrange the negative terms, you will have plus here and you will have minus here. Still the equation is valid, and the solutions will be Bessel I n of r and Bessel k n of r. So you may think Jn of ir, yn of ir are also solutions, right? They are also solutions. But see, Jn of ir and yn of ir does not need to be real. When r is real, they don't need to be real. They will be like a complex form, like just f plus ig kind of form, both of them. So we just need the real. When it is the input is real, we want the output also to be real, at least for the positive real numbers. So that's why we made new functions in and kn, whose output will be real if input is real, at least for positive real numbers. Okay, so but still they are related. Of course, Jn, Yn, In, Kn, everything is related. There is some relation connecting all of them. Okay, so now why I explain this story is that if you see this equation, let's say this is equation 2. Equation 2 resembles, okay, now it is not resembling, so you can do a transformation here. Let's say r by or r into, sorry, rho is equal to r into n plus 1 square root. So basically I am dividing throughout by the this is a number, right? It's a constant. I am dividing throughout by that number. So then grouping with r and or grouping with r square and terming it as a new variable rho square, so that there should be another quantity rho, which is r times square root of n plus 1. So if I do that, I will get d square u tilde by d rho square plus du tilde by d rho minus u tilde equal to 0. Just do the transformation. Okay, let's say this is 3. Now you see the equation 3, and let's say this is equation 4, and you compare them. Okay, there is a mistake. I forgot to put the row here. Okay, yeah, there is a row. Yeah, now it is fine. Yeah, now we compare 3 and 4. You will find, so basically the variables are now different. So u tilde is equivalent to y, rho is equivalent to r when you compare 3 and 4. Okay, but still if you compare, the form of the equation is same, just that you will find when n is 0 they are matching. But this will not happen if you compare this particular equation with 3. That's why we need the modified version of the Bessel equation. It's not the normal Bessel equation, it's just the modified version of the Bessel equation. That only will work. Yeah, here also I forgot something. Y is there, okay. Yeah. So we will find that n equal to 0, we will get the solutions. That is, then if n is equal to 0 is valid, that n is equal to 0 represents the equation 3, the Bessel equation 3. So then the solution u tilde, it will have two solutions, in and k, but n is 0, so you have I0 and k0, but the parameter is not r but rho, right? So which is r times n into n plus 1, and similarly we will have k0 r times square root of n into n plus 1, which is basically rho. I'm writing in this format. A linear combination of both is needed, C1 and C2, because it is a homogeneous equation. Equation 3 is a homogeneous equation. We don't have any extra part. This is the solution. But now comes another thing. We need to apply the boundary condition. So first of all, so I just want to ask, at least this part is clear? Any doubt in this part? Okay, so if no doubt, then we will continue. So yeah, so the boundary condition is given at u a comma theta. It's like the value of u at r equal to a, and at any theta is given as f of x. So that is a boundary condition at r equal to a. But r equal to 0 also we need to apply the boundary condition, because we need two boundary condition to solve for the constant C1 and C2. But only one is given, so where is the other one? So that's why I told we should remember that it should be a bounded solution. So at r equal to 0, it should not be unbounded. Why it is important here is that the solutions I0 and K0, one of them is actually bounded quantity at r equal to 0 or r tending to 0. Another one is actually a logarithmically divergent quantity when r tending to 0. So you see K, Bessel K is actually divergent when r tending to 0, and I is not divergent. So K0 of r in the limit of r tending to 0 is infinite, but I0 of r not infinite, 0 is tending to 0. Oh, not 0, I think. Yeah, it's bounded. So basically, for bounded solution, at r tending to 0, we need to have, so we need to basically eliminate the k function, the k0. So for that, z2 should be 0, should not be there in the solution. Thus the solution will be just c1 times I0 times r times square root of n into n plus 1. Okay, now we have to find the c1. Use the boundary condition given, which is basically u at r equal to a at every theta is given as f of x. So that means, okay, this is f of x. In the transformed variable, the u tilde at r equal to a again, but every n is some f tilde of n, which is the transform of f, the Legendre transform of f. So if we do that, let's say this is equation 6, then equation 6 will give f tilde of n if you apply the boundary condition, which is c1 times I0 at r equal to a, right? So it's a times square root of n into n plus 1, and you will find c1 is just f tilde of n by I0 of a times square root of n into n plus 1. Now if you substitute this back into equation 6 again, you will find u tilde is f tilde of n times I0 r square root of n into n plus 1 by I0 a square root of n into n plus 1. So this is the solution in the transformed domain. Now we can invert it using the definition. So this is basically u tilde, which is a function of r and n, but we want u as a function of r and x or r and theta, whatever. So we need to invert it. So we will use the basic definition f tilde of n I0 of r square root of n into n plus 1 by I0 a square root of n into n plus 1, then Pn of x into n plus half, which is basically 2n plus 1 by 2. But this is not an integration but a summation for n equal to 0 to infinity over all the positive integers. So yeah, but this is a series basically. It's difficult to evaluate it. I mean, in terms of numerically we can evaluate faster compared to an integral, but analytical evaluation will be a little bit complicated. May not be x is a closed form solution, but we have the solution. Okay, so is it clear? Okay, so if no doubt, we will move to another question. Yeah, so if mod x is less than 1, find the Legendre transform of x raised to n. So we need to use the Legendre polynomial. So it's n order Legendre transform, where we are using the Legendre polynomial is order n. So that's the question. So we'll just use the basic definition. Okay, so options are given. So because probably you can try it for a moment and let's see, can you do anything, any progress, and after that I will explain. I will wait for a moment, and so in case if you find the answer, you can put in the chat window or unmute yourself and try. Or if you have any suggestion also how to proceed with this question. So as a starter, I may explain how how it will look like. It will become an integral. How it will look like. So the Legendre transform by definition for any function is given as f of x times Pn of x dx integral minus 1 to plus. So I guess this is everyone know this. This is just a definition, right? So now thing is that here our function is just x raised to n itself. No, I'm saying n is also included in the function. So this will become minus 1 to plus 1 x raised to n Pn of x. So it's basically for every polynomials we can use this if mod x is less than 1. Okay. So from this point, how will you proceed? So if you see the options, every option will look like ms. Lot of factorials are there, factorial squares are there. So how will you reach there from here? So basically Pn of x has a lot of definitions. So which definition will you use to reach final solution, which can be look like a, b, c, d, whatever the actual solution is? So how will you reach there? Any suggestions? Okay, so if no suggestion, then I mean, if you people are trying out, you can of course try, and if you find the answer, just put in the chat window. Meanwhile, I will try to explain how you can do this from my side. Okay. Um, so Pn of x is a solution of the Legendre equation, differential equation. So, but that definition will not help here. Okay, I mean, not directly, probably indirectly we can reach some part of solution. And Pn of x has another definition in terms of the derivatives. So it's like proportional to the nth derivative of 1 minus x square, uh, something like that. I don't remember exactly. Yeah, but that also not going to help here too much. See, this is an integration, and we need to substitute for Pn of x, or you can use some part that integration by parts. Then you convert to Pn derivative, Pn double derivative. Then use the properties of Pn double derivative in terms of Pn derivative. So those things maybe you can try. I haven't tried them, but they may also work. But on easier thing that I have thought will helpful in getting the answer easily is using a definition of Pn of x, which is Pn of x as a series. So it's given us 1 by, okay, let me check the definition. Yeah, so it's actually a summation. So for m equal to 0 to capital M, minus 1 the whole raised to m, 2n minus 2m factorial, x raised to n minus 2m, the whole divided by 2 raised to n, which can be taken outside the summation also because it's not depending on m. So then m factorial, n minus m factorial, then n minus 2m factorial. So this is the definition, one of the definition for Pn of x, where m is an integer which can be either n by 2 or n minus 1 by 2, or generally it's a floor function of n by 2. So it will be valid in that sense. So I will just replace the capital M with the floor of n by 2. So those who are watching the lecture videos, Professor has already explained, not explained, just mentioned this definition. So this is complicated to remember, but this exists. Okay, now if we substitute this in equation 1, let's say. So 2 in 1, we will see the Legendre transform of Pn of x is, oh sorry, not Pn of x raised to n, is minus 1 to plus 1 x raised to n, then summation small m equal to 0 to n by 2 minus n the whole raised to m, 2n minus 2m factorial, x raised to n minus 2m, the whole divided by 2 raised to n, m factorial, n minus m factorial, n minus 2m factorial, then dx, the integral of x. Now we will interchange the orders, like integration we will take it outside and summation will go inside. Okay, so summation m equal to 0 to n by 2, the floor function of n by 2, and so whatever which is independent of the integration variable, which is basically x, we can take it outside of that and keep it in just inside the summation. So it's minus 1 the whole raised to m, 2n minus 2m factorial divided by 2 raised to n. So even 2 raised to n I can keep outside the sum also, because it does not depend on m as well, right? But I will just keep it there, it's fine. M factorial, n minus m factorial, n minus 2m factorial, then This x raised to n will join with this x raised to n minus 2n. So that will become x raised to 2n minus 2n. I'm integrating this from minus 1 to plus 1. Now the basic definition of integration. Okay, we need to do the normal integration. Before that, I just need to write this prefactor. So you know the integration of so it's just x raised to a. So x raised to a plus 1 by a plus 1, where a is a constant or a number. So here it's x raised to 2n minus 2m plus 1 by 2n minus 2m plus 1. And the limit we need to apply for x equal to minus 1 to plus 1. Because this is just a number, I took it outside the limit as well. Now if you see, n is some integer, m is also some integer. So 2n is even number, even integer. 2m is also even integer. And difference between even numbers will be another even number, right? So that x raised to 2n minus 2m, so the 2n minus 2m will be an even number always. And you are adding 1 to that, so that will be odd number. So the power of x in that expression is always odd. Remember that. Now we are applying the limit at 1 and minus 1. So 1 does not care. Any power you give, it will be give 1 only. But minus 1 cares that. Minus 1, if it was even, should have given 1. But here we have odd as a power. So that means it will give minus 1. And you are subtracting them, the upper limit and lower limit. So 1 and minus 1, you are subtracting each other. So that will get added and you will get the answer as 2. So basically, this is m equal to 0 to n by 2. Minus 1 the whole raised to m, 2n minus 2m factorial. Then the limit is giving 2 here. Then 2 raised to n here, m factorial here, n minus m factorial here, n minus 2m factorial. I write it clearly. N minus n minus 2m factorial, 2n minus 2m plus 1. Because you already applied the limit, it is 2, right? That 2 can cancel one other 2 in the denominator. So this is how it will look like. Now a little complication. This we don't know a closed form solution. Most of us don't know, but it has a closed form solution. Thing is that we may need to remember them, or we have to check in the table of the summations which include the factorials. This has a closed form solution, and it will look something like, okay, let me write that. 2 raised to minus n root pi n factorial by n plus half factorial. So that's the closed form solution, because over m it is getting summed up. So the final result should be a function of n, and now you get a function of n. But issue is that it is everything is in terms of factorials. So factorial is fine, but you have a half factorial here, n plus half, because n is an integer mostly. That's what. So the issue here is that n plus half factorial. We need to convert it to some. See, I mean, this is actually solution, but even if we check the options, we don't have something that look like exactly like this. Okay, so we need to convert it to an integer factorial, because everything here, A, B, C, D options are integer factorials if n is an integer. But even if n is an integer, the solution here given is not an integer factorial, because it have an integer plus factorial. So we will use Gauss's formula, I think, for so first of all, convert this to a gamma function, 2 raised to minus n root pi. The normal numerator, no issues, because it is integer factorial. Denominator, we can write it as gamma of n plus 3 by 2 by adding 1 again, right? Then that is actually equal to n plus half times gamma of n plus half itself using the properties. Or you can write x factorial is equal to x into gamma of x. That's another way of saying same thing. That's what we did here. Now gamma of n plus half has you have a formula for that, which is 2n factorial root pi times 4 raised to n factorial. You substitute that here, you will get 2 raised to minus n root pi n factorial by n plus half times 2n factorial square root of pi 4 raised to n factorial. Now you see the 4 raised to n and 2 raised to n will combine together, 2 raised to minus n will combinedly give 2 raised to n. This root pi will cancel, then n factorial will group together, we will get n factorial square. Then denominator you have 2n factorial multiplying 2n plus 1 by 2. So the 2n factorial times 2n plus 1 will give 2n plus 1 factorial. The extra 2 in the denominator of the denominator will go into the numerator. Join into 2 raised to n will go into 2 raised to n plus 1. So you have 2 raised to n plus 1 times n factorial square by 2n plus 1 factorial itself. So that is option C, I think. So that's the solution. Okay. So is this clear? So basically what we have done here is that the method is just a substitution for the Pn of x and then doing the normal integration. We had to choose a series substitution for Pn of x. The one we have chosen lead us to a final summation formula. We may not know the closed form solution, but we can look into tables and find how it look like, and we got some solution. Thing is that this is difficult to remember, and we don't know where it came from, right? That's another complicated thing. So yeah, of course this is a little tough, but in that sense, other than that, nothing is complicated. You just substitute and do it. I mean, even if you stop here also it is correct, but thing is that you exam time or assignments, you need to have final closed form solution. You can always look it into the table of summation, the reference books, and you will find it has some closed form solution. Okay, so no questions, we'll move to the next problem. Okay, so it's an identical problem. So if mod x is less than 1, again find the Legendre transform of nth order for the function exponential of ax. So looking similar, function is different, but still the exponential function you can always write it in terms of polynomial function. So we'll try that, right? So exponential of ax by definition is exponential of ax times Pn of x dx integral minus 1 to plus 1. Now like earlier we may okay, before that, so we will expand exponential of ax as a series. So 1 plus x square over 2. Let me write it generally. So actually ax is the variable, so it's ax the whole raised to k by k factorial sigma k is equal to 0 to infinity, then multiplying Pn of x dx. So I can reverse the summation and integration so that the summation k equal to 0 to infinity, and the constants will be outside of the integration. So it will be a raised to k by k factorial, then minus 1 to plus 1 x raised to k Pn of x dx. Okay, so this we know, right, from the earlier problem. Now we don't know, because we have found the specific case when k is equal to n. So this is actually Legendre transform, so we can write it like, okay, let me write here itself. This is actually the Legendre transform, nth order Legendre transform of the function x raised to k. But we have found something when k is xi equal to n. What is the solution? Which is we have found to be equal to that factorial. But here the solution for this one will be a function of both n and k, and we haven't found that yet. So we will find that also. Similar to the earlier case one, just that expressions will be a little different. Evaluations will be same. So let me write this as expression 1. So now we want minus 1 to plus 1 x raised to k Pn of x, Legendre transform of x raised to k. So we will use the same definition of Pn of x. So it's x raised to k times Pn of x was the summation m equal to 0 to n by 2 floor, then minus 1 the whole raised to m, 2n minus 2m factorial x raised to n minus 2m the whole divided by 2 raised to n m factorial n minus m factorial n minus 2m factorial, then the integration dx. So now we will interchange the integration and summation. So is summation m equal to 0 to n by 2. Then the constants according to the integration, they will come outside. So it will be minus 1 the whole raised to m, 2n minus 2m factorial by 2 raised to n m factorial, n minus m factorial, n minus 2m factorial. This x raised to k will join with x raised to n minus 2m, so that it is x raised to n plus k minus 2m dx, integration minus 1 to plus 1. So again we will write the prefactors unchanged. Minus the whole raised to m, 2n minus 2m factorial by 2 raised to n m factorial, n minus m factorial, n minus 2m factorial. Then the integration we can perform. So it's x raised to n plus k minus 2m plus 1 divided by the factor. So it's n plus k minus 2m plus 1 will appear in the denominator. In the numerator we have x raised to n plus k minus 2m plus 1, but the limits are applied from minus 1 to plus 1. Now the thing is that unlike earlier where k was also equal to n, so they will join together, will come to n. So here that will not happen, but you will have n and k will be added, and depending on the nature of k and n, you will have variety solutions. So one thing for sure you can say, 2m will be even. So 2m minus 2m is also even, plus 1 will be odd. So that will be always odd. So then the n plus k will remain like that, and depending on the value of n and k, that will determine what it should be when you apply for x equal to minus 1. For 1 you will always get 1. So you apply the limits, you will get something like m equal to 0 to n by 2 minus 1 the whole raised to m, 2n minus 2m factorial the whole divided by 2 raised to n m factorial, n minus m factorial, n minus 2m factorial, n plus k plus 1 minus 2m. In the numerator it is just 1 minus the value of that quantity x raised to n plus k minus 2m plus 1 evaluated at x equal to minus 1. And we know the minus 2m plus 1 will always give minus 1. That minus 1 will join with this minus 1 will become plus 1. Then the remaining factor we don't know, which is what it minus 1 will become. when it is raised to n plus k. That depends on the n and k. Okay. If both are even, both are odd, you will get even. If either one of is odd and other is even, you will get even. And so that's how it will goes. So yeah, here also we stuck. We don't know the solution for this. Of course, the summation will look identical to what we have earlier. Just that this factor is just a constant according to summation. Okay, this factor does not care summation. Modification of summation is just that we have a k which is appearing here only in the summation, because the whatever k appearing here does not affect summation, because this is actually a prefactor. We can take it outside. It's a constant. But the k appearing here, we cannot do that. That will influence the n. So just that this factor was earlier n plus 1 minus 2n. Now it is modified as n plus k plus 1 minus 2n. So it's just modification to what we had earlier. And if you do that, you will find a similar expression. It is actually, let me write that. So you have the constant prefactor, which is 1 plus minus 1 the whole raised to n plus k. Okay, that's a constant. Then the remaining part is going to give a summation, and that summation will look like 2 raised to 1 minus n, k plus 1 by 2 factorial, because remember k was 1 earlier, so this was just 1 earlier, and then n plus k, sorry, k was 0 earlier, sorry, so that's half factor, which is pi earlier, sorry, pi or something related to pi, square root pi, then k plus 1 factorial, which is earlier it was just 1 factorial, then n plus k plus 1 by 2, which is n plus half earlier factorial. So this is how it will look like. Now if you apply that in equation 1, so sub in, let's say, okay, we call this as equation 2, sub 2 in equation 1. So then you will find that this will so you will get Legendre transform of exponential of ax. So you will get a similar series. So now this factor should be this expression in 2 should be multiplied with the a raised to k, then divided with the k factorial. Then you have to take a summation from k equal to 0 to infinity. Again we start. We have a summation over k. N is fixed number, but over k you have summation. Also complicated. So what we do is we look into the tables and we'll find it actually resembles the modified Bessel function. So that's how we find the solution. So for the moment I will write the solutions 2 pi by a square root of that times I times I n plus half of a, where I is the modified Bessel function, one of them, which is of n plus half, non-integer, it's a half integer order of a. So or you can do this also in Mathematica. If you type this expression and do the summation, you will obtain these expressions. From xn point of view, it will be a little tough. These kind of questions may not appear, but other than that, like assignments and all, you can try this. Okay. So any question on this? Okay. So we have a limited time. I thought I will explain at least one problem from the last week, which I missed to explain. So this also I may not go through details, but I will just explain how you can do this. The Hilbert transform of the function f of t given by sin t by t square plus 1. So by definition, the Hilbert transform of how we will take the function, right? Sin t by t square plus 1. Let's say t to x, you are taking the Hilbert transform. You should do like 1 by pi times Cauchy's principal value integral from minus infinity to plus infinity, the function divided by t minus x dx. That's all the integration. Now this integral is difficult to solve, so you have to move to complex plane. And when you have sin t cos t, you will always choose the function in the complex plane to be e raised to it. Generally, t square plus 1, then t minus x dt. Oh, it's actually not ds, sorry, it's a dt. So t is the integration. Now you do the contour integral over a closed contour, and here you should choose the contour to be, so see the integration needs a different color. So in the complex plane we have real of t here and imaginary of t here. Now the singularities for this particular function, see e raised to it is an entire function, don't have any singularities. T minus x has a singularity, or 1 by t minus x has a singularity at t equal to x. Let's say some x can be positive or negative but should be real, so it will be on the real axis. Then 1 by t square plus 1 has two singularities at plus I and minus I. Both are on the imaginary axis. So we have minus I here, plus I here, and x here. For every value of this t, we will have singularities. And we want the integration to be performed over along this real axis from minus infinity to plus infinity, skipping the value at x. So what we'll do is we'll skip this. Let's say we skip through this way. Doesn't matter, we can skip it down also, does not matter. We have to modify the equations little bit accordingly. So that's fine. But now the other closing is important. The larger closing, we can close it in the upper half or lower half depending on the solution will get affected. So it's e raised to it. Earlier class I have explained there is a question which is similar, has an exponential of I omega t. And if you remember, when omega is greater than 0, similarly here, if you consider omega is here, it's omega is 1, which is greater than 0. We close it on the top half plane. Then only the integral over that arc will converge to 0. Otherwise, it will diverge at infinity. So we want it to be, the contribution from that arc to be vanished, at least finite. For that, we need to close it to the upper half. So if it was exponential of minus it or some number times t, it, then we should have closed it down. So because we have this factor is exponential of plus it basically, so we need to close it in the top half. And let's say this has radius r. Let's say this has a radius of epsilon. So we will I'm not showing explicitly, you can okay, this is a contour, and let's say this, I'll call this contour as let's say gamma, and each of this has simple names. Let's say this is arc, and this is a line 1, and this is a line 2. There is arc 1 and arc 2. So arc 2 you can choose it to be down also, does not matter, with epsilon tending to 0, but you have to modify equations a little bit, because now if you write this expression over gamma, it is 0 because not 0, it's by Cauchy's theorem, it's a 2 pi I times residue of the function at t equal to I alone, because I is the only singularity which is inside the contour. Even minus I is outside this contour, x is also outside this contour. But if we have included this x inside by drawing this like this, instead of the upper you close like this, then x will counted inside. So you have to have on the right hand side 2 pi I times the residue at I plus residue at x. In the left hand side you will have integration which is performed, so right now the integration will be performed from 0 to pi, but if you have closed it in the other way, it will have, sorry, it's not 0 to pi, pi to 0. But in the other way, you should have done it from pi to 2 pi. So that's the difference. So basically negative. So they will cancel each other. The contributions, whatever way you took, will cancel and you will get finally. Cancel means there will be a cancellation and you will get the appropriate answer only. Does not matter. So here we will go with this at least. So what then you the integral over gamma you can split in integral over arc 1, arc 2, and line 1 plus line 2. Similarly, you will be so you can show that integral over arc 1 in the limit of capital R tending to 0. You can show that is going to vanish, and integral over arc 2 also you will find there exists some finite contribution, and integral over line 1 plus line 2 will together become basically this Cauchy's principal integral. Then this residue also you can evaluate. So residue will be just multiply. Okay, let me show that residue of exponential of it by t square plus 1 times t minus x, because at t equal to I it's a simple pole. You multiply with t minus I and then take the limit of t tending to I. You will find it will be e raised to I into I, which is minus 1, by here it will be just t minus I, okay, t plus I is 2I times I minus x. So that you can convert it to real form by multiplying with the conjugate and numerator and denominator. Then you will have a contribution from the this smaller circle, where you assume t to be, so over arc 1 you can say it is going to vanish. Over arc 2 you will say integration is performed over t, which is actually shifted circle, x plus epsilon e raised to I theta, epsilon tending to 0, where theta is going from pi to 0. In the limit of epsilon tending to 0, you will find there is a finite contribution from that integral. So like that you can find the solution. So I'm just leaving in here, so you can try this out and find the solution. It's actually simple, but I just thought I will explain this. Okay, so any doubt in this? Okay, so if not doubt, so we'll stop here for today. So next week we'll meet again. Okay, thank you.